If you had to guess which resource shortage would most directly threaten your ability to get an MRI scan, disrupt the manufacturing of the chip in your phone, and ground a rocket launch, all at the same time, helium is probably not the answer that comes to mind. It should be. In March 2026, roughly a third of the world's helium supply disappeared essentially overnight. Here is a fact that makes this genuinely different from the most other commodity shortages. Helium can be manufactured. It is a byproduct, extracted almost exclusively from specific natural gas fields where geological conditions happen to trap it. And once released into the atmosphere, it escapes Earth's gravity permanently. There is no recycling it back from the air the way you might recover other materials. What exists in the ground is functionally all there will ever be, extracted at whatever rate those specific gas fields allow. In early March 2026, strikes on Qatar's Ras Laffan industrial city, home to the world's largest liquefied natural gas complex and the source of roughly one-third of the world's helium supply, destroyed a significant portion of the country's export capacity. Qatar Energy suspended helium production entirely, stating operations would resume only once shipping security through the surrounding waters was assured. Qatar had been producing approximately 63 million cubic meters of helium annually, out of roughly 190 million cubic meters produced globally, supply that went offline immediately and has remained offline indefinitely since. Spot markets prices for liquid helium have roughly doubled since the disruption began. What makes this shortage so consequential rather than merely inconvenient is how many critical applications have genuinely no alternative material available. Medical imaging, superconducting MRI, magnets operate at temperatures approaching absolute zero, and liquid helium is the only substance capable of maintaining that temperature in a clinical setting. Without it, an MRI machine simply can't function. Semiconductor fabrication, advanced chip manufacturing requires ultra pure inert atmospheres during wafer processing, and the specific thermal and chemical properties helium provides at the purity levels required for the most advanced manufacturing nodes can't be replicated by nitrogen or argon. Aerospace, helium pressurizes rocket fuel tanks and purges propellant lines before launch. And increasingly, quantum computing, helium cools the superconducting processors quantum systems depend on to maintain operational stability. To make that stakes concrete, industry analysis estimates that domestic semiconductor producers in several major economies are operating on approximately 6 months of reserve helium inventory, meaning a supply disruption of this scale doesn't create an abstract long-term planning problem. It creates a countdown clock measured in months before facilities are forced to actually curtail production. Taiwan, given its concentrated high-volume chip fabrication base, faces a comparable dependency region, which means this helium disruption compounds directly with the semiconductor concentration risk we have discussed elsewhere in this series as well, rather than existing as a separate, unrelated problem. This is not, in fact, the first time the world has faced helium crisis. It's more accurate to call this the latest in a recurring pattern stretching back 2 decades. An earlier shortage around 2006 was triggered by plant outages colliding with rising demand from the fiber optics and semiconductor industries. A second, around 2012, stemmed from political uncertainty over the future of the US Federal Helium Reserve, a strategic stockpile built during the Cold War and stored underground in Texas, which for decades effectively buffered the global market against exactly this kind of shock. That American reserve, once the world's dependable backstop, has since been drawn down and largely privatized, removing a buffer the market quietly relied on for generations without most people ever being aware it existed. What's what's the difference or what's different about the 2026 shortage is much lesser the shock itself and more the fact that the strategic cushion that's used to absorb these shocks no longer exists in the same way. One of the more uncomfortable second order effects of this shortage is that it has put previously unrelated industries into direct competition for the same limit resource. Hospitals requiring liquid helium to maintain MRI magnets and semiconductor fabrication plants requiring it for wafer processing are in a genuinely tight supply environment, now biting against biting against each other, along with aerospace and quantum computing users, for allocation from the same shrinking pool of suppliers. Reporting from mid 2026 indicates that facilities lacking adequate reserve capacity have begun rationing MRI operational hours, while some fabrication plants have reduced throughput or shifted to less helium-intensive manufacturing processes where technically feasible. This is precisely the kind of cross-sector source competition that rarely gets modeled in single industry risk assessments because under normal conditions, these industries never had reason to think of themselves as competitors for anything. The response on the supply side illustrates how quickly a genuine price shock can reshape exploration incentives. Primary helium exploration projects, meaning field developed specifically to extract helium rather than a secondary byproduct of natural gas extraction, are now advancing in locations including Tanzania and Minnesota, specifically because they are geographically decoupled from the volatile natural gas markets that have historically determined helium's fate as an afterthought byproduct. Canada has also emerged as an increasingly insignificant new source. None of this new capacity comes online quickly. Exploration and extraction infrastructure for a resource like helium is a multi-year undertaking, but it represents a genuine structural shift. For the first time in decades, helium is being treated by investors as a resource worth developing in its own right, rather than simply hoping it shows up as a convenient byproduct of gas production aimed at other markets. The most immediately actionable response, though, doesn't require new extraction at all. It requires capturing helium that's currently simply being wasted. Both MRI facilities and semiconductor fabrication plants have historically vented significant volumes of used helium directly into the atmosphere rather than recovering it, largely because for most of the last several decades, helium was cheap enough that recovery infrastructure wasn't worth the capital investment. Modern closed-loop recovery systems can now capture and liquefy up to 90% of helium that would otherwise be lost. And the math on that investment has changed dramatically. At pre-crisis prices, the paycheck period for recovery infrastructure was long enough to discourage adoption. At prices that have roughly doubled, industry analysis describes the return on that same investment as having become, in their words, unarguable. Japan's Ministry of Economy, Trade and Industry has also already implemented subsidy programs specifically to accelerate this recycling infrastructure build-out. For most of the last century, helium was treated as a curiosity. Cheap, seemingly inexhaustible, too trivial a resource for serious strategic attention. A single disrupted facility on a single day in March 2026 was enough to reveal exactly how much quite load-bearing weight that trivial gas was actually carrying across medicine, technology, and space exploration simultaneously. It is a small, oddly specific case study in a much larger pattern we keep encountering across the series. The infrastructure most critical to modern life is very often the infrastructure we've spent the least time thinking about, right up until the moment it isn't there. Thank you so much for your attention and your presence, and I'm really looking forward your questions, your reflections, your interactions. If you have any comment or feedback, feel free to leave them as well. Make sure I read each one of them and I will reply once I can. And I'm really looking forward to welcome you in another lecture. Thank you once again for your presence. Till next time.